Lesson 20, activities. Let's find some derivatives using our brand new trig derivatives list, as well as the chain rule. So part A, derivative of cosine of stuff is negative sine of stuff. Be really careful about the negative, don't miss that one. Negative sine of, you copy the stuff one time, and then the chain rule says times the derivative of the stuff. So 27x squared minus 8x plus 7. Okay, and then the next one, part B, first thing to do is write this as a power, sine of x, and then the fifth root and seventh power really means to the 7/5 power. And so we'll take our derivative here, y prime equals, this is stuff to a power, so the power rule says the power comes down, copy the stuff, subtract 1 from the power, and then times the derivative of the stuff in the parentheses, and the derivative of sine x, we now know, is just cosine x. C. Secant of x to the 5th plus 3x. Secant of stuff becomes secant of the stuff times tangent of the stuff. So secant of the stuff times tangent of the stuff. It's kind of weird that we have to write this stuff twice, whereas normally we just copy this stuff once, and then times the derivative of the stuff in the parentheses. 5x to the 4 plus 3. So again, derivative of secant has two things in it, secant and tangent. So that's why we had to copy the stuff twice, once for each of them, and then one time at the end, times the derivative of the stuff. Okay, part F looks like a product rule to me, x squared times some other function of x. So here's our product rule. First, times the derivative of the second. So derivative of tangent of stuff is secant squared of the stuff times the derivative of the stuff. So that's the first part of the product rule, plus the second times the derivative of the first. And we'll throw it in parentheses, and that's our answer. Make sure you don't think that that this is the product of three things. It's x squared, and it's tan of x to the 5th plus 3x. This is one thing. Right? It's not tan times x to the 5th plus 3x. It's tan of x to the 5th plus 3x. Okay, part E, for sure this is a quotient rule. Y prime equals, so just so I don't forget, I'm going to put the bottom squared. Okay, quotient rule says bottom, so we copy that, times the derivative of the top. The derivative of sine of stuff is cosine of stuff, times the derivative of the stuff in the parentheses. And the derivative of e to the x, we saw in a previous class, is just e to the x. Continuing the quotient rule, minus the top, we copy that, times the derivative of the bottom. So the 1 plus becomes 0 plus, which I won't write. And then the derivative of cosine of stuff is negative sine of stuff, times the, oh, that's not right, 4 to the x on the bottom. Negative sine of stuff times the derivative of the stuff. And the derivative of 4 to the x is 4 to the x, but remember this is an a to the x example. So it's not as simple as specifically e to the x. We always have to multiply by ln of the base, ln of 4 in this case. Okay, this one actually does clean up, but we're not going to do any simplifying here. So we'll leave it as is. All right, so all of this is is E, and then F we'll do down below. Okay, so that guy, I'll just recopy it, but I'll write it as a power. Y equals x to the 3rd plus cosecant of x, and then the square root we know is a 1/2 power. And so now we'll do our derivative. I see stuff to a power. Let's use our notation. We'll change it up and use Leibniz's notation just for kicks. So the power comes down. Copy the stuff. Subtract 1 from the power, and then times the derivative of the stuff in the parentheses. So x cubed plus becomes 3x squared plus. And then the derivative of cosecant is actually negative cosecant cotangent. So I'm actually going to change this to a negative cosecant x tangent of x. And that's the end of this one. But to be honest, it could have been more complicated. If this had been something more complex than x, then you would have copied it there, and then you would have put its derivative over here. So like if this had been, for example, x squared, this would be x squared, this would be x squared, and then times a 2x right there. I think I might have just lied. I did just lie. It wouldn't have gone there. It would have gone inside the parentheses. Yeah, that's where it would have had. It would have to only be attached to the cosecant cotan. Okay, I think we're good. All right, number 2, a little trick thanks to a former student of mine named Ashley for remembering and not losing track of like the signs of the derivatives of sine and cosine. Okay, so she wrote this little thing that we're going to call a ladder, and it always is exactly this same collection in this order. Sine on the top, then cosine, then negative sine, then negative cosine. And so she discovered that the derivatives go this way. And so if you wanted to know the derivative of sine, you would just say, okay, I'm going to find sine here, and it just goes right down there. Derivative of sine is cosine. And if you want to know the derivative of cosine, you just find cosine and go one rung down the ladder. So derivative of cosine is negative sine. Now, if you wanted to know what the derivative of negative sine of x is, you just go one rung down the ladder and get negative cosine x. And if you want to know the derivative of negative cosine, you just loop back around. This ladder goes forever with many copies of those 4 things in that order. So the derivative of negative cosine is positive sine, and then it repeats. And so we can figure out very quickly the 7th derivative of negative sine x without actually going through the hassle of doing 7 derivatives. So starting with this one and then going down the ladder, there's my first derivative, 2nd, 3rd, 4th, 5th, 6th, 7th, cosine x. Okay, so what if it were something bigger, like not 700th, but maybe the 753rd? You could use division, right? This thing just loops around in cycles of 4. And so if I asked you for the 753rd derivative of negative sine of x, I'd like you to be able to do it without too much effort, without counting it all out clearly, like we did there with the 7th derivative. Okay, number 3. So we're given this formula for the depth of water, and we're going to find dy dt. So that's the derivative of this equation. The 5 plus disappears. 4.9 is a constant multiple which stays. Cosine becomes negative sine. Copy the stuff. And then times the derivative of the stuff in the parentheses, which is pi over 6. Okay, so there's my derivative, and it says, what does this thing represent in terms of water level? So let's write a sentence. Dy dt represents the rate of change. Let's go ahead and write the units here. Measured in, and the units we remember for a derivative are just the units of whatever letter is on top over the units of whatever is on the bottom. The y units were feet, and the t units were, where is it? Hours. So this is measured in feet on top and hours on the bottom, feet per hour. The rate of change of water level as a function of time. So it's the number of feet per hour that this water level is changing, rising or falling as time passes. Okay, so then it says for 0 to 24, when is dy dt equal to 0? When is it 0? And let's explain what it means for dy dt to be 0. Okay, so we're going to take our blue thing and set it equal to 0. So 0 equals this negative 4.9 and all the rest. Okay, we're going to solve this for t. As usual, the first step is to get the trig function part by itself. So we'll divide by negative 4.9 and also divide by pi over 6. But the nice thing is the 0 doesn't care about any of that. And so we just get 0 equals the sine of pi over 6t. Okay, and 0 equals sine. 0 is on our unit circle. It's one of our nice labeled points. So remember that the sign on the unit circle is the y coordinate. So you're thinking about that unit circle and you're thinking about places where the y coordinate is 0. I guess we can just go back and find it real quick. Here it is. So places where the y coordinate is 0, I see 1 right here and 1 right here. And so my answers, like my two fundamental answers are 0 radians and pi radians. Okay, so from the unit circle, we've got two answers. Either 0 radians is equal to the angle, pi over 6t, or pi radians is equal to the angle, pi over 6t. But remember, and I said, you know, there's almost always two fundamental answers. But remember, there's really infinitely many answers because we could lap around the unit circle 83 times before finally landing on pi. And so this is, again, the part where we add the plus 2 pi n to both of them. And then we will multiply both sides by, we're going to solve for t, so we'll multiply both sides by 6 over pi. 6 over pi times the 0 is still 0, plus 6 over pi times the 2 pi n is just 12n, the pi's cancel. 6 over pi times the right-hand side gives just t. Same deal here, 6 over pi times both sides. 6 over pi times the pi is 6, plus it's the same 12n here, and it's the same t right here. So here's our double infinite family of solutions, and we're looking for all the places between 0 and 24, including both. And so this one, if you let n equal 0, gives you 0. If you let n equal 1, gives you nothing plus 12 times 1, or 12. If you let n equal 2, nothing plus 12 times 2 is 24. If you let n equal 3, you would get 36, which is a perfectly good solution, but it isn't between 0 and 24. So those are our three answers there. And then this one, if we let n equal 0, gives me 6 plus nothing. 6 is good. Letting n equal 1, 6 plus 12 times 1 is 18. Letting n equal 2, 6 plus 12 times, 6 plus 12 times 2 is 30, which is outside of our interval, 0 to 24. So here are our 5 solutions, 0, 6, 12, 18, 24. Oh, were we supposed to answer something else? Explain what it means for dy dt to be 0. Okay, so at these moments in time, the water level isn't changing. At these 5 times, the water level isn't changing because the rate of change is 0 feet per hour. Now, if you go not to the 6-hour mark, but to 6 hours and 1 second, well, now the water level is changing. So I'm really talking about just these 6 frozen moments in time. And so I guess also probably that means that some of these 5 numbers are like maxes of the water level. You can imagine the water level rising and falling, and so maybe this is like 6, and maybe this is a 12, and maybe this is an 18. I'm just making it up. We could draw the graph more accurately if we wanted to. And so horizontal tangent lines, the water level is briefly frozen up there, something like that. Okay, number 4, herd of population is given by that. How fast is the population changing at t equals 0.75? So how fast, that is for sure a derivative. So we got to calculate p prime of t, and then we'll plug the 0.75 into this thing. 4,000 plus becomes 0. 500 times the constant multiple stays. Sine of stuff becomes cosine of the stuff, times the derivative of the stuff in the parentheses. That is 2 pi plus nothing. Okay, so there's my derivative. And then we're going to plug in t equals 0.75. So p prime of 0.75 equals, let's bring the 2 pi into the front. So this is 1,000 pi. Cosine of 2 pi times 0.75. plus the pi over 2. Now, we could just bail out and type this onto the calculator. Maybe we should do that. I don't know. But I actually think something nice is happening here. So this is just saying 3/4 of 2 pi. So that's 1.5 pi, or 3 pi over 2. And then plus the pi over 2 gives me 4 pi over 2, or 2 pi. So anyway, when all is said and done, I think this results in just 1,000 pi cosine of, what did I say? Is it 2 pi? I think that's right. 2 pi, 1.5 plus another half is 2. Yeah. And then cosine of 2 pi is something nice, right? It's just 1. And so this whole thing is just 1,000 pi. So could do that without a calculator. If you typed it into the calculator without doing any of this simplifying, you'd obviously get the decimal version of 1,000 pi. And so roughly something like that, 1,000 pi. We could put some units here, right? This is the derivative. So that means it's the output units over the input units. This is the population per year. So deer per year. So that means that the population is growing at roughly 3,141 deer per year on October 1st, at that one moment in time. Okay, when in the interval 0, 1 is the deer population at a max, and what is that max? Okay, so to find the maximum, I guess we need to take the derivative and set it equal to 0. So 0 equals 500 cosine 2 pi t plus pi over 2 times the 2 pi. Again, first step here is to get cosine by itself. So we divide both sides by 500, divide both sides by 2 pi. 0 laughs at both of those things. And so we just get this. And so thinking about where the cosine is equal to 0, so we did up above where the sine was equal to 0, so we're not going to go back to the previous page, but on the unit circle, we know that cosine is the x-coordinate, looking for points on the unit circle where the x-coordinate is 0. So I'm envisioning the top point on the circle and the bottom point on the circle. And so that's going to be the two angles pi over 2 and 3 pi over 2. So pi over 2 is one of them, is equal to the angle. And then the other one is 3 pi over 2. Okay, but again, after you find your two fundamental angles, you've got to remember to put in the plus 2 pi n, because we could loop around any number of times and just land on one of these right fundamental spots. Okay, so as usual, basic algebra to solve for t. I've run out of space here, so I'm going to bleed into the next problem with this. Okay, so solving this first equation here, right there, for t, we're going to subtract the pi over 2. Oh, that's nice. The pi over 2's go away. And then we're going to divide both sides by 2 pi. Divide both sides by 2 pi. Actually, that was so nice maybe that we don't even have to bleed into the next one. So this one, I think, you just get t equals n. Any integer will be a solution to that original 0 equals equation. And then over in this other equation, it's not going to work out quite as nicely, but that's okay. We're solving for t. So we subtract the pi over 2. Subtracting that gives you pi. And then we divide both sides by 2 pi. Everything divided by 2 pi. So I think we're going to get the pi divided by 2 pi is a half. Plus, and then this red thing divided by 2 pi is just n. So here's the other infinite family of solutions, half plus an integer. And then the first family of solutions was just the integers. And so the answers between 0 and 1, the candidates anyway, would be t equals 0. That's an integer. T equals 1. You could go to t equals 2. That's a solution to the equation, but it's not between 0 and 1. We could go to -1. That's also not between 0 and 1. And then over here, if you let n equal 0, you get half. If you let n equal 1, you get 1.5, which is outside of our 0 to 1 interval. You can let n equal -1, you get -0.5. That's also outside of 0 to 1. So I think these are our three solutions to the equation. but it's not guaranteed that all three of those are maxes, right? Like probably one or even two of them are mins. And so we really do need to think about how to find out whether these guys are mins or maxes, which are which. So let's do our standard real number line. So we've got 0, and we've got 1/2, and we've got 1. I think that's good. And we got to be really careful when we're plugging in here because there are other solutions that are just off of the grid. Like 1.5 is right there, and that's a good solution, and -1/2 is there, and so you can't go past those because you might change the signs. So we're going to be really careful. I'm going to use a calculator here and pick numbers that are very close to these three numbers here. Okay, so something a little bit less than 0. And what am I plugging into? I guess we're plugging into the derivative here. Remember, we always labeled the sign charts with the function that it came from. And this function was called, what was it called? P? Yeah. So P prime is what we're plugging into. So something a little bit less than 0. And we're plugging into P prime, which is given by this green thing right here. And so we're going to do 500 times cosine of 2 pi. And again, we hit the cosine button, so we check our mode. Make sure you're in radian mode. 2 pi times t. Okay, I haven't picked a t yet, but I got to pick something slightly less than 0. How about -0.1? For sure, that's not too far because -1/2 was the next number that isn't marked on this one. So that's my t plus the pi over 2. Close those parentheses and then times 2 pi. I don't care about the number per se, I just care about whether it's positive or negative. So okay, very much positive right here. And then between 0 and 1/2, how about we pick positive 0.1? So I'm just going to do exactly the same thing here, but get rid of this negative sign. Okay, great. So it's going to be a plus here, then a minus here. I'm guessing it's just going to alternate, but let's make sure. In between here and here, we'll pick 0.6. So change this to 0.6. Plus, minus, plus, great. And then right on the other side of 1, we'll pick 1.1. So we're going to insert a 1 there. 1.6 would be no good. We're going to do 1.1. Plus, minus, plus, minus. Lovely. Okay, so what does that mean about P? It means that P is increasing and then decreasing and then increasing and then decreasing. And we were looking for the maxes. And so I see a max at 0 and another max at 1. It didn't ask us for it, but there's a min at 1/2. Okay, so we got our maxes, and then finally, what is that maximum? So I think it's just asking for P of these of 0 and 1. So P of 0 is equal to, and I think P of 1 is going to be the same thing because I think our period here is just 1. All right. 2 pi. Yeah, so the period is just 1, so it'll be the same thing. So if we plug 0 into the original, so 0 right here for t, so this part becomes nothing. So this is pi over 2. Sine of pi over 2 is 1. 500 times 1 is 500. Plus 4,000, we get 4,500. So that is when the population is at a maximum at 0 and 1 year, and the maximum population is 4,500. Okay, part C wants to know when in the interval 0, 1 the population is growing the fastest. So the growing population is clearly a reference to P prime, and I want P prime to be as big as possible, the fastest. So I'm trying to maximize P prime, which means take its derivative and set equal to 0. So that's our process. So we're going to say that all of this goes with the question above. Think to there. Okay, so yeah, good. All right, so we're taking a derivative of p prime. So p prime is right up here in black. So we're doing a derivative of that thing. I'm going to save a little bit of writing. This 2 pi we know we could have shoved into the 500, so that's really 1,000 pi. Derivative of cosine, that's going to change to a negative sign of the stuff, but then times the derivative of the stuff. So the derivative of this stuff is another 2 pi. So we're going to get another 2 pi coming out here with the 2 pi that's already there. That was 1,000 pi times another 2 pi is 2,000 pi squared. That was a lot that I said, so rewind if you missed it. P double prime of t, 2,000 pi squared. Okay, it was cosine of stuff. Now it becomes negative sine of stuff. And the stuff was 2 pi t plus pi over 2. And then times the derivative of the stuff in the parentheses. That's a 2 pi, but I've already absorbed that 2 pi in here. Really hope I did that right. Just make sure for my own sake here. Okay, so we're going to get another 2 pi coming out here. That's a 4 pi squared times this 500 is a 2,000 pi squared. Money. All right, so we said we were going to take this derivative and set it equal to 0. So let's do that right here at the end. Equal to 0. Solving this equation first involves getting the sine part by itself. So we divide by negative 2,000 pi squared. 0 stays 0. That's nice. So we get sine 2 pi t plus pi over 2 equals 0. Okay, so same deal as before, equaling 0. That's a nice number on our unit circle. Sine is the y coordinate on the unit circle. So we're thinking of the unit circle and finding the 2 spots where the y coordinate is 0. And those 2 spots are the 0 angle and the pi angle, the far right-hand point on the circle and the far left-hand point. So from the unit circle, either 2 pi t plus pi over 2 is the 0 angle, or 2 pi t plus pi over 2 is pi. Those are our 2 spots, but those are just representative of the infinite family of spots. So this is the moment we do the plus 2 pi n on both, and then we'll solve these 2 equations. Okay, so in the first equation, we're going to subtract the pi over 2. 2 pi t equals negative pi over 2. I guess that's it. The plus 0 I won't write. And then, plus the 2 pi n. And then divide both sides by 2 pi. So the 2 pi hits both terms on the right-hand side. T equals negative. So when I divide by 2 pi, the pi's cancel, but the 2's do not. This is negative a quarter. And then when I divide the 2 pi n by 2 pi, we just get plus n. Okay, I like that. And then here, subtract the pi over 2. 2 pi t equals, so pi minus pi over 2 is pi over 2, plus the 2 pi n. Divide both sides by 2 pi. We get t equals, so again, dividing the pi over 2 by 2 pi, the pi's cancel, but the 2's work together. We get positive a quarter here, plus divide 2 pi n by 2 pi, and we get plus n. So here's our double infinite family of solutions, here and here. And we just need to pick the values of n that will land those orange things in the interval 0 to 1. Okay, so in the first one, if we let n equal 0, we get negative a quarter. That's no good. If we let n equal 1, we get 3 quarters. So t equals 3 quarters is the answer here. If you let n equal 2, you'll get 1 and 3 quarters, which is outside of our 0 to 1 interval. And the next one, you let n equal 0, that gives you t equals 1 quarter. And if you let n equal 1, you get 1 and a quarter, which is, again, too big. So these are our 2 candidates. But specifically here, we were looking for places where the population is growing fastest, and then when it's decreasing the fastest. So one of these is a max, and the other is a min, and we just have to figure out which one is which. So let's do our standard sine test calculation. So here we go. We've got 1 quarter. We've got 3 quarters. And these numbers came from p double prime, so that's our label. And we're just going to do our quick sine test on the calculator. So there's p double prime in orange at the top. So we're going to plug things into this orange guy. So the negative 2000 pi squared we'll type here. This is 0. Times sine, again, make sure you're in the right mode. We're still in radians, Ruby, 2 pi x. But in this case, we're going to put in a number that's just a little bit less than a quarter here. So that's 0.25. How about 0.24? That feels safe. Even 0.2 is good. We just need to make sure we don't get past the negative a quarter, which is the next one over here that we didn't mark. So 0.2 is good there. That's the t plus pi over 2. And we just care about whether that's a positive or negative. So negative there, and then we're picking something between a quarter and 3/4. How about 0.5 there? 0.5 here. So negative, positive, and then something bigger than 3/4. How about 0.8? So it was negative, positive, negative again. Great. Negative, positive, negative. That means that the function that is one level up from p double prime, which is to say p prime, was decreasing and then increasing and then decreasing. So for p prime, 1/4 is a min and 3/4 is a max. Okay. All right, so on the next page, we're going to prove this derivative rule using some trig stuff. Hopefully we still know. Okay, we're going to prove that the derivative of tan is secant squared, and the hint is to rewrite tan as a quotient of two other trig functions. And we know that tan is really sine over cosine. That's just a pre-calc thing, no calculus. I've just copied the derivative symbol. And now we're going to take the derivative of sine over cosine using the quotient rule. So the bottom is cosine squared. I'll write that. That's cosine of x, the bottom squared. And then we do the quotient rule, bottom times derivative of the top. So we copy the bottom times the derivative of the top. The derivative of sine x is cosine x. Minus the top, copy the top, times the derivative of the bottom. The derivative of the bottom, derivative of cosine, is negative sine x. Equals, okay, cosine x times cosine x. That's cosine squared of x. I'll write it that way. Negative sine x times another negative sine x is positive sine squared of x. And then I will rewrite the bottom as cosine squared of x. Do not cancel the cosine squared x's. That's no good. But there is a Pythagorean identity. It's written right here. Hopefully you remember that one. That sine squared of x plus cosine squared of x is 1 for any angle x, which means the numerator here, even though it's in the reverse order, is just 1 over cosine squared of x. But remember, 1 over cosine is a different trig function, right? 1 over cosine is secant. But this is really 1 over cosine squared. So, of course, this is really secant squared. And so there's our proof that the derivative of tan x is secant squared of x. Okay, and then moving on to number 6, says we're going to rigorously prove that the derivative of sine is cosine, but we need two limits that we're going to guess the values of based on looking at tables. So first one is the limit as h goes to 0 of sine of h over h. So what I have done here is given you screenshots from my calculator. There's my sine of x over x. And I've picked particular values of x. I'm trying to go near 0. So 0.1, 0.01, for some reason 0.006. I get an error at 0, of course, and then we get some negative values that are near 0 as well. So what appears to be happening to these outputs? Well, goodness, they sure look like they are heading to 1. So not rigorous proof, but compelling evidence that perhaps the limit of sine h over h as h goes to 0 is exactly 1. Same deal for the other limit. We're looking for the limit of cosine h minus 1 over h as h goes to 0. So I've given you more screenshots. This is a table for the function y equals cosine x minus 1, all divided by x. That's supposed to match this guy. And again, we pick x's, h's, heading towards 0 from above and below. We get the error in the middle, but what appears to be happening to these numbers here? Well, negative 0.05, negative 0.005. This one, remember this e really means times 10 to the, so this is really negative 5 times 10 to the negative 4, which means take that decimal point and move it 4 places to the left. So negative 0.005 is there. And then we're just making our guess what appears to be happening to these numbers. Well, it sure looks like they are heading to 0. And again, it's not a rigorous proof, but evidence that perhaps this limit is exactly 0. It turns out it is. Okay, these two limits are the reason calculus is done exclusively in radians. So I guess it bears mentioning here. We're trying to prove that the derivative of sine is cosine, and that is true as long as the angle x is in radians. But if the angle is in degrees, then the derivative of sine of x is not cosine of x. The derivative of sine of x is cosine of x times pi divided by 180. And I would much rather deal with cosine of x than cosine of x times pi over 180. So let's see if we can prove that the derivative of sine is cosine in radian land. Okay, we know the definition of the derivative. We saw this a while back in this course. Limit as h approaches 0, f of x plus h minus f of x. So in our case, the f of x is sine of x, and so f of x plus h is sine of x plus h. And then f of x is just copied here, sine of x. Everything else is copied. A trig identity that we're going to bring in from your pre-calculus days, sine of a plus b is really sine a times cosine b plus sine b times cosine a. We're not going to prove that one here, but hopefully you saw it and you believe it from some previous class. But we're going to use that to expand out this part of our derivative calculation. So sine of x plus h, according to our formula here, well, all we're going to do is we're going to change the a to an x and the b to an h, right? Now it looks like sine of x plus h. So sine of x times cosine of h plus sine of h times cosine of x. Great. So putting it together, the derivative of f is this limit right here, and all we're going to do is change this thing to what we just figured out it was equal to. So equals sine of x cosine of h plus sine of h cosine of x minus sine of x all divided by h. I'll continue to highlight. Hopefully it'll be clear. So the green highlighted stuff is there, and then we'll highlight in yellow. The other part was just this minus sine of x, and that one is just copied over here. Okay, so I'm going to do the next step on this page just so I don't have to recopy. But on the next page, it tells you you're supposed to head towards a certain thing. So let's see if we can get there on this page. Equals limit as h goes to 0, big fraction. Okay, what we're going to do is split this thing up. I'm going to reorder the terms. I'm going to copy my first term, like that one where it is. But then I'm going to move the minus sine x up here. Actually, why don't we do two fractions? And then I'm going to do my second term over here, sine of h cosine of x. And it's two fractions added together. Both of them have this denominator. So pause if you need to. Make sure you believe that this is indeed equal to the one fraction we had before. Because if I asked you to add these two fractions, you'd say, oh great, they have the same denominator, so I can put them into a single fraction. And all I've done then is just shuffled the three terms around. They're still here. 1, 2, and 3. Okay, in the first limit, we are going to factor out the greatest common factor on top. Technically, I should have big brackets around this whole thing because it's all inside of the limit. So equals limit h goes to 0. Okay, so we're factoring out on top sine of x, and then we're left with cosine of h minus 1. And that whole thing is divided by h. And then plus, I'll just copy this one as it is, sine of h cosine of x all over h. And again, big brackets around the whole thing. We're going to do one more little trick here. and that's just to peel off parts of these numerators. So here we go. Limit h goes to 0. All right, I'm going to write it, and then you're going to hopefully believe it. Sine of x times the fraction cosine of h minus 1 over h plus cosine of x times the fraction sine of h over h. Big brackets around the whole thing. So hopefully you buy it. This sine of x is really over 1, and if you had to multiply these fractions, you'd put that sign on the top, multiply it, and you'd put the 1 on the bottom, and that's exactly what we had before, right? And this cosine is really on the top. Yes, it is, and there's a 1 with an h, sure. Okay, and now finally, I get something good. This thing should look familiar. It is inside of a limit as h goes to 0. And we guessed up above, looking at that table from my graphing calculator screenshot, that the limit as h goes to 0 of cosine of h minus 1 over h is 0. That was our guess. And so this piece goes to 0. Now this sine of x looks like it's a variable quantity, but it isn't. The variable for this limit is h. Sine of x is just a constant. It is completely unmoved when h goes to 0, or h could go to anything. Sine of x doesn't care what h is doing. So this is really just sine of x times 0, and I'm not putting the limit anymore because we just sent h to 0. Okay, let's take a look at the other one. So over here, this thing should also look familiar. It's inside of a limit. It's a limit as h goes to 0 of sine of h over h. And we guessed, looking at the graphing calculator screenshot, that this fraction went to 1. And again, this cosine of x is unmoved by h going to 0 because there's no h's in it. So this is really cosine of x times 1 with a plus sign in between. And so the sign vanishes, and cosine of x times 1 is just cosine of x. And remember, the very first thing that we started with in this long calculation was f prime of x. That is the derivative of sine, is what we have been calculating this whole time. And so the derivative of sine of x, indeed, is cosine of x. You can prove that the derivative of cosine is negative sine doing a similar thing. We're not going to do it here.